Okay, Young's double slit experiment is one of the two experiments you need to know about. The other one is the diffraction grating experiment. Now with this experiment here, you can see that we have a single slit, okay, and we have a double slit set up, and there's a screen over here, okay. Now the waves come in, so you can see all these here are parallel waves. They come in and they bend due to diffraction, okay, so there's that circular wave pattern due to diffraction. And then the waves are in step as they go through these gaps. There's the double slit here. And we then get the pattern like we just looked at before with the overlapping waves. Now, you can see along here, that point, that point, that point, that point are all crests, and so they then have constructive interference there. Along there, we've also got constructive interference, and along here. Now, so that means there is a bright spot there, and there's another bright spot that will be out there, and off the page down the bottom, and another one there. Now, this is what you see is essentially on the screen will be a interference pattern, so a series of bright spots and dark spots. So here, there's regions of destructive interference where there's a crest and a trough at the same time, and you get nothing all the way along here. So even if you move the screen in, you'll still get a pattern similar to this. Why do we use a single slit? Well, that's because we want a coherent light source. In other words, all these waves here are emanating from one source, so they all must be in phase. Okay, there's not two waves that are continually changing their phase together. And when they go through here, they're in step as they go through. Okay. So diffraction will occur at each slit, okay, and a series of fringes or bands will be formed on a screen. The central maximum is the zero path difference. The first order maximum is essentially when the path difference is either 1 times the wavelength or 2 times the wavelength, and so on. Now, this is what you would see on a screen if you're trying to laser through a double slit. You'll get a pattern that looks like this. So you have a central maximum, and then you have n equals 1 there, n equals 2, n equals 3, n equals 4, and so on. And on this side you'll have the first order, second order, third order, fourth order, fifth order. Remember, this one here in the middle is called the central maximum. And here's an actual photo of what you'll see. Okay, so this is with a slit separation here of 0.02 millimeters. You get that sort of pattern, and you can go to a slit separation there of 0.16 millimeters. You can get that pattern. Well, where are the path differences? So let's look at a double slit. Okay, so it's going to be quite a poor drawing, but hopefully we can get the idea. So as that laser beam, if we look at the distance from there to the screen, okay, so I'll put a screen on here as well. So there's our double slit, and here's a screen, and what we're going to do is we're putting light from those two slits to that screen. Now, let's say we had two crests going through this gap, okay, so two crests at that time, like the wave goes like that, and the wave goes like that, so they're in phase. Now, for us to have a constructive interference here, they need to be in phase. So if we go to the middle, essentially both waves have traveled the same distance, so they're always going to be in phase. Here, the waves have traveled a certain distance, so the top wave will be like that. Now, for it to be constructive interference, the other wave also has to be like that. Now, what that means is actually this one here, so the wave from here needs to actually travel a wavelength longer. Okay, so let's put it like this. So if we have a wave like this, okay, and I'll just draw another wave, and another wave like that. If we want to get these things back in phase again, we have to move them by a whole wavelength like that. Okay, so if I just continue on that black one, then it will be in phase again. Okay, so if I move that green one forward by a whole wavelength, then it goes back in phase and you get another bright spot. So that's one wavelength difference in length. The next one will be 2 wavelengths difference. So where is that length? Well, it would be about here, okay? And let's say we do a line across like that. Then the difference in length there is 1 wavelength, okay? So that length there, it's called path difference, will be equal to 1 wavelength. Now we know the slit separation here is W. Okay, let's change pens, sorry about that. So the slit separation there is W. Okay, or sometimes it's also called A. Okay, it depends what book you read. W or A. So that's the length of that side there. Lambda is the length of that side. And if we knew an angle here, we could then do some calculations, okay? You don't have to concern yourselves with the actual derivation of the formula. You just have to understand that because this path difference here is 1 wavelength at the first order, then you'll get constructive interference. At the second order up here, okay, the path difference, in other words, how far, oh, get rid of that, how far the wave went from this one compared to this one is now going to be 2 wavelengths. Okay, so there's another wavelength there. So, what's the formula for Young's experiment? Okay, if we go back to this diagram here, this separation here we'll call A. Okay, distance there, let's call that capital D. And we're going to have some bright spots on the screen. Okay, like that. Okay, and the distance between those is going to be X. The distance from the single slit to the double slit has no meaning. The distance from the source to that double slit has no meaning. Okay, so let's have a look at the formula. Wavelength of light is lambda. Slit separation was A. Distance between adjacent maxima, okay, that's X. Distance between slits and screen, that is D. Okay, so the formula is lambda equals AX over D. Okay, now let's just think about this for a second. If I double the wavelength of light and I keep my slit separation and the distance between the slits and the screen, so I keep this one and that one the same, what's going to happen to X? Well, because of the equals, the other side must also go up. So that means the spacing between the maxima is also going to go up. Okay, can you see that? So double the wavelength, you then double the spacing. If you double the distance from the slits to the screen, okay, keep this side equal to 1, because we've just got to keep lambda, we're not changing that. Then we have to then double X, okay, so this fringe separation will double. If we double A, the slit spacing, then in fact we must shorten, or reduce our fringe separation. And you can see that back on these images we had here. So as we increase our slit separation, we then actually get a smaller fringe spacing according to that formula. So the next thing is called diffraction grating. So diffraction grating is essentially it's like a grill. You imagine like a storm drain. It's just like a grill, but there are many lines or many holes per millimeter. Okay, so what happens here? We have multiple slits instead of just a double slit, so there's many slits. So in other words, we actually get something that's a bit more pronounced. Okay, so a lot clearer than what a normal double slit would be. So the ratio between N and D, okay, well N is the is equal to the number of lines per essentially meter, okay, Usually it's given to you in millimeters, so you have to be very careful looking at that. And D is equal to the distance in meters between them. Okay, so D is the distance in meters between the lines. Now, just to get from one to the other, let's just do a quick little example. Let's say I had 1, 2, 3, 4, 5 lines, and the distance between them, the distance here is 1 meter. Okay, and let's say the separation between them. Okay, how do we find that out? Well, all we need to know here is that there are 5 lines a meter. Okay, there's 4 gaps in a meter. So what we're going to do then is just do 1 divided by the number you have, and you then get D, the distance. Okay, so in this case, it's going to be 0.25 meters. Okay, when you do these calculations with diffraction gratings, it's a little bit different because N is typically something like 300,000 lines in a meter. So it's a little bit of a different number, that's all. Same principle as double slits apply, although maxima is much more pronounced, as I said before. So here we got N equals 1. Okay, this one here, the one that's always straight ahead, N equals 0, N equals 2, and N equals 3. So you can see that the wavelength path difference is also important, just like in the double slit. And here's an example of this. So for you to get constructive interference, things have to be in phase. So in this case here, see these two waves are now back in phase. So to do that, you need to actually change by 1 wavelength. And essentially the formula is shown there, how to derive the formula. Another example of it. This one's probably a bit clearer. To get another bright fringe, we need to go by a change in distance lambda. And D is that side, that's the distance between 2 slits. And theta is the angle there. Okay. Now, so after you've done all that, what's the wavelength for light? Well, it's always lambda. Slit separation, okay, in this case it's D. Angle of diffraction, okay, so this is the angle from the center, okay, angle of diffraction from central, okay, I'll just write central, takes too long, okay, so that is, remember the straight fringe, or just one that you just want to choose, in fact, N is equal to the order of diffraction. Remember, N equals 0 straight, N equals 1 is the first one to the side, N equals 2, and so on. So the formula in this case is N lambda equals D sine theta. Okay. Now think about this formula. Let's say we want to double the wavelength. Okay. What happens to the other side? Well, D is a constant. Okay. N's a constant. Let's look at the first order. So what's going to change? It's going to be the sine theta. Okay. So to get sine theta double, we just need to double the angle. So essentially, this side then also, so the theta is then going to go up, okay, to make 2. Okay, so double. So you need to look at how that changes. Okay, what we have here is a diffraction sort of setup, okay, for the first question. So which one of these is going to diffract the most? Let's just ask ourselves that. I want to draw it. But this one here, the slit size closely matches the wavelength, so this will have the greatest curve. Remember, this one here is going to have a straight bit in the middle and curves at the end. Now looking at question 2. A house in a small valley can receive an AM radio signal on 1200 kilohertz, but doesn't receive the FM station on 91 megahertz. Now, which one of these has a longer wavelength? It must be the AM. Okay, has a lower frequency, so it has a longer wavelength. Okay, the shortest wavelength is the FM. Now, use the ideas of diffraction to explain why. So remember, a small valley essentially is some sort of someone's living down a hole. Okay, so there's your house. Now, what you need to get is you actually need to get some sort of diffraction around the bend here. So you've got your radio waves coming along and they need to diffract down like this. Okay, so the house can actually hear it. Well, not hear it, but receive the signal. So for that to happen, you need to think about the wavelength. Now, so the longer the wavelength, the greater the diffraction. So this one here will diffract the most, well, this one here won't diffract as much. Okay, so the 91 megahertz may, in fact, as it comes along, let's make it a bit longer, will diffract slightly, but it won't be enough probably to hit the house.